Sometimes we're less concerned with how much position changes and more with how quickly it changes. This video is going to introduce the concept of velocity. We're learning to describe the rate of change in an object's displacement with time so we can describe its motion in terms of velocity. We know we have it when we can describe an object's velocity verbally, visually, mathematically, and graphically. We've all likely heard of the terms speed and velocity and have probably used them interchangeably, but it's important to know the difference between the two. Speed is distance traveled divided by time. Speed is a scalar because it only has magnitude, meaning it only has a number that describes its size. Velocity is a vector. What makes a vector different from a scalar? Its direction. Velocity has magnitude and direction. In fact, it may be helpful to think of velocity as speed in a given direction. The direction allows us to predict future positions. We can define velocity as a rate of change in an object's position, and we can represent it with the mathematical equation v bar equals delta x divided by delta t. The v bar means average, so our equation is average velocity equals displacement divided by time. And we measure velocity in meters per second. So what do we mean by average velocity? Your velocity likely changes as you travel from point A to point B. You speed up on the highway, slow down for stop signs, that sort of thing. So if we were to graph it, it may look something like this. This would be your instantaneous velocity. The speedometer on your car shows you the instantaneous speed, but not velocity because it doesn't include direction. But there's always some velocity which will allow you to make the same trip in the same time without speeding up or slowing down. And this is equal to your average velocity. When speed and direction don't change, we can say that velocity is constant. When speed and direction don't change, we can say that velocity is constant. And your average velocity is equivalent to the constant velocity needed to make the same trip. So let's take a minute to express velocity graphically. We've already discussed position versus time graphs, where position is on the y-axis and time on the x. The last thing we said was that the slope of these graphs show the rate of change in an object's position. So for an object at rest, its position doesn't change, so the slope is 0, which is just a flat line. In this example, for an object moving with constant positive velocity, the position increases in a positive direction, and the rate of change is constant, which is why we have a straight line there. For a constant negative velocity, we just have the opposite. For a graph of position versus time, the slope is equal to the velocity. So in the first case, our velocity was 0, so we have a horizontal line. In the second case, we have a positive constant velocity, so our line has a positive slope and it's straight. And in the third case, we have a negative constant velocity, so our line has a negative slope and it's also straight. You may remember from math class that slope is equal to rise over run, which in this case is our change in x over our change in time, which you may recognize as the equation for average velocity. Another type of graph that we can use is a velocity versus time graph, where velocity is on the y-axis, time on the x. An object at rest has 0 velocity, so our graph is a line along the x-axis. If it's moving with a constant positive velocity, our line is above the x-axis. And notice that it's a horizontal line now because the velocity doesn't change. And that line will be below the x-axis if it has a constant negative velocity. These graphs can show displacement as well. The area under the graph equals the displacement. We've talked a little bit about constant velocity. We'll talk about when velocity changes in the next video.